Section 1.5 is complex numbers, and we run into complex numbers when we try to solve equations which, let me give you this example. If I say, what do you square and get 9, you tell me what? And not only 3, but also -3. So that has two solutions. They're both real numbers, +3 and -3. And as long as that was the scenario, x squared equals a constant, nobody ever needed complex numbers. But someday, one day, somebody encountered this and tried to answer the question, what can I square and get -1? Well, I'm not sure why anybody needed that solution, because I haven't done enough applied mathematics in my life to know what you build with imaginary numbers. I know two career fields that use them are electrical engineers and submariners. If you become a engineer on a submarine, you need to know about imaginary numbers. Now you're nodding like you have some familiarity with that. Tell me what you know.
I'm going to be an electrical engineer and I've taken pre-calculus before.
Okay, all right. And so did your other teacher have any more experience with imaginary numbers to say, here's where you use them?
Yeah.
Give me an example. Was that Mr. Bolden?
No.
No.
I was homeschooled, so I learned from a guy named Craig Clark.
Fantastic. And he had used imaginary numbers?
He gave us more of examples of not real numbers on an imaginary number line that went off of non-existent directions.
Okay. If I had invented imaginary numbers, I would call them something other than imaginary, because that sounds like Barney making them up. And it was actually not Barney. It was, I think, maybe Leonardo Euler. I've actually forgotten who invented the notation. But there was no real number that satisfied that equation. No real number you can square and get a negative. But this dude said, I gotta have something that would stand for the square root of a negative number, and that's where the notation was invented. Math is not invented. Math has always been exactly what it is, but as we learn more about math, we invented more notation to describe what's happening. So somebody said, let's use a new symbol, I, to stand for the square root of -1. From now on, whenever I see the square root of a negative number, I'm going to know that it's an imaginary number. And the very few people on the planet need them, but the ones who do keep nuclear submarines running and your lights coming on. That allows us to simplify something like square root of -36. I know there's no real number I can square and get -36, but if I wrote that -36 as 36 times -1, what's the square root of the 36? What's that?
Well,
6.
well, yeah, but all the way out.
No, it's not 5 minus 1, it's the square root of 36 is 6. The square root of -1 is I. That's 6i.
That's what I said.
I thought you said 5.
No.
You said 6i, and I heard the I sounded like 5. That's why I was sick this morning. Yeah. And calculus this morning, it was just like, oh, can I make it 30 more minutes? All right, Samantha, I'm sorry I didn't hear you correctly. But we're going to write square root of -36 as 6i. So let me see on page 57 and 58 if there's anything beyond what I just scribbled at the top of my paper. We have the definition of the imaginary unit I. From now on, I just takes the place of square root of -1. Since that's the definition of I is the square root of -1. If we square both sides of that equation, squaring the I would give us I squared. squaring the square root of -1 gives us -1. From now on, whenever we see a I squared, we're going to put -1 in its place. So all the kinds of numbers that we know of either fall into the category of real numbers or imaginary numbers. Real numbers and imaginary numbers are all the numbers there are. If we put those two subsets together, we have the whole universal set of numbers, which is the complex number system. Any number, real or imaginary, can be written as a complex number in the form a plus bi, where a and b are real numbers. A is the real part, bi is the imaginary part. So if I just ask you to write the number 3, the real number 3, as a complex number, you could write it 3 plus 0i, because it doesn't have an imaginary part. Or if I ask you to write the number 2i as a complex number, you could write it 0 plus 2i, because it doesn't have a real part. Here are other examples of complex numbers. Plain old 3 is a complex number because it could be written as 3 plus 0i, 2 plus I is a complex number, plain old 2i is a complex number. We add complex numbers by adding their real parts and adding their imaginary parts. If I didn't tell you I was anything special, but I just gave you 2 complex numbers to add, you would just combine like terms even without knowing that I was anything special. When you multiply 2 complex numbers, you just FOIL them as if you didn't know I was anything special. Except for when you get to the next to the last step, when you FOIL that out and you get an I squared, what are we forever going to put in place of the I squared? -1, and then you can simplify it some more. So that's how we operate on signed numbers. My one example of that I want to work out with you is 3 minus 2i cubed. What does it mean to cube something? Multiply it times itself 3 times. Maybe ugly, may turn out not to be quite as ugly as I'm expecting it to be. When I see a binomial times a binomial times a binomial, I think, oh, this is going to be awful. But let's see if it actually is. Any, mini, miny, mo, it doesn't matter which 2 you add first, or excuse me, multiply first. You want to multiply these first 2. You multiply that by FOILing it out. Go ahead and multiply 3 minus 2i times 3 minus 2i. Simplify it as much as possible and then stop right there. Here's what I got when I multiplied 3 minus 2i times 3 minus 2i. But before I multiply a trinomial times a binomial, that would actually take 6 multiplications to multiply a trinomial times a binomial. I don't have to do that because this trinomial simplifies to what? Yeah, that I squared is -1. This is the same as 9 minus 12i minus 4. That's just 5 minus 12i. So I don't know why I wrote a negative. 5 minus 12i times 3 minus 2i. It's just a binomial times a binomial again. So go ahead and multiply those 2 and simplify as much as possible. What does that simplify to?
-9 minus 46i.
Yep. Because again, that I square is -1. So 15 minus 24 is -9. -9 minus 46i. Is it the same thing if you write -46i minus 9? Would this be okay for an answer? Yeah. That's just the commutative property of addition. It doesn't matter what order you write those in, as long as you're adding a -9 and a -46i, you can add them in whatever order you want. This is what we consider standard form, and that's what the answer will be, how the answer will be written in the back of the book, the real part before the imaginary part. All right, so you can add, subtract, and multiply complex numbers. My B part here says rationalize the denominator. What has that meant to us so far? Give me an example that might say rationalize the denominator. Exactly. If we had 1 over square root of 2, math books, for some reason, don't leave radicals in the denominator. Well, number 26 doesn't have a radical in the denominator, but yet the directions say the same thing. Rationalize the denominator, because I is not a rational number. I is not even a real number. You don't leave radicals or imaginary numbers in the denominator, but you simplify it the same way you would if that was a radical you were trying to move. What could you multiply that fraction by that would cause its denominator to become a rational number? Yeah. If you, and not just I, but whatever you multiply the denominator by, you have to multiply the numerator by the same thing. But if you multiply that by I over I, then the denominator is going to become 3i squared. And what is that? That's -3. So when we finish that numerator, we will have rationalized the denominator. The denominator is a rational number now. The numerator, make sure you distribute that I completely. I times -2 is -2i. And I times 6i is what? Yes. I'm putting 6i squared, and I'll simplify it in the next step. You have -2i plus 6i squared, and then in the place of the I squared, we're putting -1. So that's -2i minus 6, and the denominator is rationalized. Why is that not going to be the answer in the back of the book still? I was really concerned more about the negative in the denominator. Math books just don't leave a negative in the denominator. If you factor that negative out of the denominator and distribute it through the numerator, that becomes 2i plus 6 over +3, and that's just simpler than all of those negatives. That's probably still not the answer in the back of the book, though, because the directions say write your answer in the form a plus bi. If I divided that 3 into both terms, what would my real part of the answer be? 6 over 3, better known as just 2. And then what would the imaginary term be?
2.
It's probably going to be written as 2/3 I. Divide the 3 into both terms, and then write your answer in the form real part plus imaginary part. All right. So in the section that we were talking about radicals, we said if you give me 1 over square root of 2, for example, how am I going to rationalize that? Multiply by square root of 2 over square root of 2. That's when the denominator is a monomial, but what if the denominator was a binomial? Then what did we have to multiply by? What's that word? Oh, not opposite, but conjugate. You multiply by the conjugate, which for this would be square root of 2 plus 5. So that the outer and the inner terms would cancel and you wouldn't have a radical in the denominator anymore. Yes, how we take care of that? Well, first let's take care of the radicals all together. We can just get rid of them if we write square root of negative 121 as what? (11i). We could write that numerator as 5 minus 11i, and we could write the denominator as what? 1 plus 5i. Do that before you multiply by the conjugate, because i's are easier to work with than those radicals. What's the conjugate of that denominator? One minus 5i. Multiply that whole fraction by 1 minus 5i over 1 minus 5i. Go ahead and do that. What you have for your first step? And when you put negative 1 in place of your I squares, tell me what you're thinking. This would be, did I make a typo right there? No, this is positive 55i squared, and then it's, gotcha, and then it's 5 minus 50. I'm glad you're keeping an eye out for me though. That's probably not the way the answer is written in the back of the book. If the directions say write in forms a plus bi, then it's just going to divide 26 into both terms and reduce it as a fraction. You could reduce the negative 50 over 26 to negative 25 over 13. And then don't forget to also divide the 26 into 36 and reduce it. That would be negative 18 over 13i. Any questions? So we can add and subtract complex numbers. We can multiply complex numbers. We can rationalize the denominator of a complex number. Let's talk about powers of I. I to the first is just I. That's just the definition of what the exponent 1 means. Anything to the first is just itself. And then what do we say I squared is? -1. How can we use those two expressions, I and I squared, to figure out what I cubed means? How could I rewrite I cubed using what's written above it? I'm going to put in one middle step, but you're exactly right. I'm going to factor I cubed as I times I squared. And then I'm going to put -1 in place of I squared. The simplest way to write that is just -I, but I wanted you to see where the 1 came from. What about I to the 4th? How can I use anything above it to help me figure out what I to the 4th is? How can I factor it? I could factor it as I cubed times I, and then just multiply those. It seems like the easiest thing would be what you said, Samantha. I can factor I to the 4th as I squared times I squared. And in place of each one of the I squareds, I could put a -1. So what is I to the 4th? +1. Now, either we're going to have to keep going forever to a value, well, not forever, but all the way up to 68 to do 16 part A, or we're going to recognize a pattern that will allow us to simplify I to the 68 faster than having to continue this pattern 68 times.
Wouldn't the even one just be a positive one after?
Where are you, Samantha? I missed the beginning of what you said.
Or like all the even or even powers?
Any even power would just be, what are you saying? Well, what about I squared? It's an even power and it's -1. That was a good thought. You have to have thoughts and then you have to test results to see if they're right. So you had a great thought. It turns out it wasn't exactly right.
You have to return.
Even powers are either 1 or -1. That's true. How do we figure out which ones are +1 and which ones are -1? If we're not sure yet, then we need to keep going a little bit farther and see if it becomes apparent.
Like
Every other even. So not 2 but 4, not 6 but 8, not 10 but 12. So far we have 4, 8, and 12. What do all those have in common? They're when the exponent's a multiple of 4. When the exponent's a multiple of 4, you can put a 1 in its place. So I to the 4th is 1, I to the 8th would be 1, I to the 12th would be 1. That's the best way to describe every other even, it's just multiples of 4. So in other words, you give me any power of I, and I'm going to factor out as many I to the 4th as I can, because I know I to the 4th is just 1. I can factor I to the 5th into I to the 4th times how many i's left over? just one. And then in place of the I to the fourth, I can put 1. So I to the fifth is the same as just I. I to the sixth, I can factor out an I to the fourth, and that'll leave how many I's? So I can write I to the sixth as I to the fourth times I squared. What can I put in place of I to the fourth? 1. And what can I put in place of I squared? -1. So I to the sixth is -1. But it's that I to the fourth we want to watch out for. If we can take as many I to the fourth out of any power of I as we can, then we can deal with the leftovers. When I get down to I to the 68th, I think, how many I to the fourth can I factor that into? I to the 68th would be I to the fourth. How many times? I think somebody said it right before the lawnmower. 17, because 4 goes into 68 17 times evenly. I can write I to the 68th as I to the fourth to the 17th. And then just double check my multiplication, but if that's right, then in place of I to the fourth, I could put 1, and 1 to the 17th is just 1. So Samantha, what you said is working. If your exponent is a multiple of 4, the answer is just going to be 1. What about I to the -33? How many I to the fourth could I factor out of that? Got an idea? 8, but that's not quite -33, that's 32. What else would I have to have? How can I get this to equal I to the -33? How could I just make that -32 instead of +32? I made the 8 negative. That's I to the -32. And then I'd have to multiply it by I to the what? It's -32 plus 1, -33. -32 minus 1. And then in the place of I to the fourth, I could put 1. What could I put in the place of I to the -1? How could I write it with a positive exponent?
Right.
1 over I. And then what's 1 to the -8? 1. And then I would be tempted to just leave that answer 1 over I. But we just said math books don't leave i's in the denominator because I is not even a rational number. Now it turns out I've made this problem harder than I meant to. There was an easier way. We're going to get the same answer, and then I'll show you the easier way. But right now we just have 1 over I, and I need to rationalize that. I rationalize it by multiplying by I over I. And that just gives me negative I. Because in the denominator, I times I would give me I squared, that's negative 1. I divided by negative 1 is negative I. That was not how I meant to do that problem. Can anybody think of another way that would have been simpler?
I to the third to the negative 11.
Tell me why that is simpler. It's certainly true. I to the third to the negative 11. And then what?
Would have been 1 over negative I.
I cubed is negative I. But it still looks pretty yucky to me right now. I'm thinking something else. Hold on a second. What if I said, what if I had said I to the negative 4 sheep? What did I want to do? I thought of something easier and then it went away. And it's not coming back. This absolutely worked. Double check yourself every step of the way. That is I to the negative 33. And that is 1 times 1 over I, but we just had to rationalize that because we couldn't leave a negative in the denominator. Your way would have worked as well. I'm just not really seeing how it's easier than this way since I still have to work on the negative I to the negative 11. Let's go on to I to the 66th. What factor of I to the 4th could we take out of that? 16, and that would give me I to the 66. Excuse me, I to the 64. So how many i's are left over? 2 left over. Double check. Does that multiply back together to give me what I started with? Yeah, that's I to the 66. In place of I to the 4th, I could put 1. What can I put in place of I squared? Negative 1. So that whole answer is negative 1. All right. I could do this B part just like I did the B part above it. I'm going to skip it because it would be almost exactly the same. I'm going to skip it and I'm going to go back to my office, and the minute I sit down, the easier way will pop in my head, because that's whatever happens when I do something the hard way in class and just get stuck. As soon as I go back and sit in my office and take a deep breath, an easier way will pop in my head. I could still do it though. If it was a homework problem, I could do it just like I did that one. Let's go on, because we have 2 other kinds of problems to mention in just 10 minutes to mention it. Roman numeral 3 is the equality of complex numbers. 2 complex numbers are equal if their real parts are equal and if their imaginary parts are equal. If a plus bi, if that complex number equals the complex number c plus bi, then a and c have to be equal and b and d have to be equal. That allows us to solve this expression for y, well actually for x and y, because this is just 2 complex numbers. On the left-hand side, x minus y is the real part. On the right-hand side, 4 is the real part. If those two complex numbers are equal to each other, then x minus y has to equal 4 because that's setting the two real parts equal to each other. What equation would we have if we set the two imaginary coefficients equal to each other? Three equals y. And I really didn't mean imaginary coefficients. The coefficients aren't imaginary. I meant coefficient of the imaginary terms. 3 is the coefficient of the imaginary term on the left-hand side. Y is the coefficient of the imaginary term on the right-hand side. So we have a system of equations, but we already know what y equals. Y equals 3. So we can put 3 in the place of y in the first equation. And find the value of x. X would have to be 7. We can check that. If we let x be 7 and y be 3, then what is the complex number on the left-hand side? If x is 7 and y is 3. It's 4 plus 3i. On the right-hand side, if y is 3, that's also 4 plus 3i. And number 8's the same thing. If you set the real parts equal to each other, 8 equals 2x, so x equals 4. And if you put the coefficients of the imaginary terms equal to each other, you have 3x plus y equals -4. Solve for y by putting 4 in the place of the x in the second equation. All right, last thing, we have some equations with complex solutions. At first glance, when I see number 48, I think, well, I can just add 27 and then take the cube root of both sides, and I have x equals 3, and it checks. So that's the answer, x equals 3, because 3 cubed minus 27 is 0. Well, if all I wanted was the real solutions, 3 is the only real solution. But whenever the directions say find all solutions, then if there are any imaginary solutions, you need to find those as well. Now, how do you find the imaginary solutions? Well, what special kind of binomial is that? In terms of factoring, we would call that what? Difference of 2 cubes? Remember that paper turned sideways that tells you how to factor the difference of 2 cubes? That's where you get a binomial factor times a trinomial factor. What's your binomial factor?
X minus 3.
Cube root of the first term, same sign, cube root of the last term, right? And then you look at that binomial factor, square the first term, then what?
Plus 3x.
Opposite sign, and then multiply the 2 terms, and then what?
Plus
Square the last term is 9. Now that I have that factored, I can set each factor equal to 0, and that's where my real solution comes from. X minus 3 equals 0 means x equals 3. But what about when I set this other factor equal to 0? What kind of equation is that? Because the x squared is quadratic. Can you factor it further? X plus 3 times x plus 3 would give me a 6x in the middle. That actually would not factor any further. And if it won't factor any further, how do we solve it? How? Quadratic formula, and I expect to get imaginary solutions, but the quadratic formula will help me solve that. A is 1, B is 3, C is 9. And just plug that into the quadratic formula as quickly as you can. X would equal negative b plus or minus the square root of b squared minus 4ac, all divided by 2 times a. That's negative 3 plus or minus the square root of, I'm going to go ahead because we're in a hurry and say 9 minus 36 is negative 27. How do I simplify square root of negative 27? How could I factor the negative 27? This is something I could take the square root of times something I couldn't. Negative 9 times 3. And then what can I put in place of the negative 9, or square root of negative 9? Yep. That won't reduce any farther. The answer in the back, they may write it negative 3/2 plus or minus 3 square root of 3 over 2 times I, because that's in the form of a complex number that they want us to write our answers, the real parts plus the imaginary parts. Just make sure you've divided the 2 into both terms. I'm going to tell you real quickly and not have time to do it, but number 56, factor that by grouping and see what happens. Number 52, again, if we get it set equal to 0, that's the difference of 2 squares. Will x squared plus 9 factor any further? No. The x squared minus 9 will, but when we set each factor equal to 0, those last 2 equations are going to give us our 2 real solutions, positive 3 and negative 3. That's the only 2 solutions we would have gotten if we just took the 4th root of both sides. We would have gotten the plus or minus 3, but we would not have gotten the 2 imaginary solutions. Plus or minus 3i. X squared equals 9, and you take the square root of both sides, you get plus or minus 3i. So that had 4 solutions. The homework is actually on the 3rd page of the notes. Just the 1.5 is what you need to finish for tonight. And 1.6 is tomorrow.